discuss here. We started with the Diractified signal. Which basically contain the discrete signal. And this is basically the Diractified signal. And we saw that the Fourier transform of the Diractified signal is given by this infinite sum which, if we define the cyclic frequency omega hat equal omega ts, we get a natural we get basically the definition of the discrete time Fourier transform. And I remind you that the x sub s of omega hat is periodic, is 2 pi periodic, or equivalent, this xs of omega is omega s periodic. Okay? And of course, this is the natural definition of the dTft of the discrete signal x sub n, which is basically the Fourier transform of the Diractified signal. Now, given this Fourier transform, we would like to recover the discrete signal. We know how to recover the Diractified signal because this is equal by the integral 1 over 2 pi integral minus infinity to infinity of xx of omega e to the j omega hat in the omega. Okay? This is basically the inverse Fourier transform of this signal here. However, we want to recover the discrete signal. So we saw that the discrete signal, which is basically the continuous signal sample at NTS, is equal to the convolution between the Diractified signal convolved with a very generic window, which has to satisfy a few properties, and computed at t equal n sub ts. Is right? Indeed, we saw that if we have here a discrete signal ts nts n plus ts n minus ts. So here we have 1, 2, 3, 4, 5, 6, 7, for example. This is the Diractified signal. I can choose, for example, the sinc function as a window. This is the let's call it w sub b, is the sinc function. Or I can choose the box function. This is wa of t. And I will be still able to recover the original discrete signal, okay? So as long as Wt symmetric, W at 0 is equal to 1, and W at nts is equal to 0 for any n different than 0, okay? And then it's pretty straightforward to given the discrete time Fourier transform of the signal, which is basically the Fourier transform of the Diractified signal, recovering the original signal, or the original discrete signal, because now I can so if this is my if I have the original Fourier transform of the Diractified signal, yeah, we can use, which is the same, I mean, yeah. Then xn, the discrete signal, is equal to the convolution between the discrete signal and the spatial window, but computed at t equal nts. And now I can do this is equal to what? This is equal to 1 over 2 pi integral minus infinity to infinity Fourier transform of this guy here, e to the j omega t d omega, but all of this has to be computed at t equal nts. Now, the Fourier transform of a convolution, I know what it is, because this is equal to xs of omega times the Fourier transform of the window. So I get, the general form x of n is equal 1 over 2 pi then of this integral, which I have to evaluate at nts. So I get integral minus infinity to infinity of xx of omega, w of omega, e to the j omega nts d omega. And this gives me infinite choices of to recover the discrete signal from his Fourier transform, discrete time Fourier transform. Indeed, we found two choices. So let me, I can choose a window, which is a box. And the correspondent Fourier transform, we know that is a sinc function, which is equal to, I'm going to write it down here, w of omega equal ts sine of omega ts divided by 2, divided omega ts divided by 2. And if or we can choose a sinc function in time, and the correspondent Fourier transform, we know that is a box of amplitude Ts. These are two choices, and of course, we will get two different expressions of the inverse Fourier transform. Which are given by this. And these are just two examples. Indeed, what we saw when we plug this expression inside here, and we define the cyclic frequency omega ts, what we found? We found that given xn, a discrete signal, I can compute his discrete time Fourier transform as the infinite sum from n equal minus infinity to infinity of xn e to the minus j n omega hat. Okay? This is the discrete time Fourier transform. Vice versa, given xx of omega hat, I can recover the original signal with the following expression. I can do, for example, the integral between minus infinity and infinity of x-axis of omega hat sine of omega hat divided by 2 divided omega hat divided by 2 e to the j and omega hat in the omega, or xn equal 1 over 2 pi integral between minus pi and pi of xx of omega hat e to the j and omega hat in the omega. And these expressions are equivalent, okay? So all these on this, they will give me the same results. Of course, I'm going to pick the one that it's easy to compute. But this other one is also valid. It is correct. They give me the same results. Actually, no. There is a, it would be interesting to be able to go from here to here, and in a very general way. And so there are infinite expressions of this inverse discrete time Fourier transform, but they always give the same results. So we still have uniqueness. There is still a one-to-one correspondence between a discrete signal and its discrete time Fourier transform. But there are infinite representations, infinite Fourier integrals representation, which they will give you the same results. Of course, the most practical one to use is going to be this. Okay? Indeed, from that's what inverse discrete time Fourier transform. Okay, so discrete time Fourier transform. But it's very important here to realize that in order to recover the discrete signal, so we need to undo the Diractification, and we have done that by convolving the Diractified signal with a window, and then sample this value at NTS. That was the key step, basically, undo the Diractification. And the way to undoing the Diractification, there are infinite choices for the window, which will give different representations, different integral representation of the inverse discrete time Fourier transform, but they're all basically the same. So we still have the one-to-one correspondence between a discrete signal and its Fourier transform. And this basically concludes the lecture. Thank you.